get out your notes, we are learning about similar polygons today. So we just finished a unit, and it was called congruent polygons, congruent figures, congruent triangles. Now we're going to move on to similar polygons, similar triangles. So let's talk about how they're similar and different, right? So notice all of these shapes, they look the same, like shape-wise, right? These are the same shapes, but these are different sizes. That's at the root of similarity, things that are the same shape, but different sizes. And we're going to look at what is the same from congruent and what's different from the congruent unit. Whose shoe is this? You got it. Shaquille O'Neal's shoe. Yes, it is. So, we're unfortunately not going to be able to watch the video. But if we were wondering how much bigger Shaquille O'Neal's shoe is than the average person's shoe is, we would be comparing them. We'd be comparing the shoe sizes. And that's what similarity and ratios are all about. Comparing. How much bigger is it? And in math, we can't just say, oh yeah, it's a lot bigger. That's what you can say in English, right? In math, we have to say how much bigger it is with a numerical answer. So that's what we're studying in this unit. Here are some words. Let me come back to that. Here are some words that are going to come up in this unit. Similar, proportion, dilation, ratio. Let's talk about these words. Similar. So we talked about that earlier. It is the same shape, but different size. That's what similar means. It's not the formal definition. It's just kind of the layman's terms what it means. A dilation, that's a transformation, like a translation, a reflection, a rotation. But a dilation is an enlargement or a reduction. So you're changing your figure proportionally, but you're enlarging it or reducing it proportionally. That's a dilation. A ratio is a comparison of two numbers. We did that in the warm-up today. 1 to 9. That's one way to write a ratio. 1 to 9. That's another way to write a ratio. And 1 to 9 is the third way to write a ratio. Now, when you take two ratios and you make them equivalent, that is called a proportion. So, for example, 1 is to 9 as 2 is to 18. And I would probably put an equal sign, but 1 is to 9 as 2 is to 18. That's a proportion. So a ratio is just a comparison of two numbers. A proportion is a comparison of two ratios. It's two equal ratios. So the ratio equals another ratio. A fraction equals a fraction. And of course, when we're missing something in our proportion, we're going to cross multiply. So these are all things that are going to come up in this unit. Who uses similarity in the real world? Like we said earlier, so similarity is derived from like a dilation. And dilations are used a lot in art. They're used a lot in architecture. They're used a lot in engineering. So here's an example of when someone took a small drawing, they drew something, and then they enlarged it. Now, if they didn't enlarge it by the same scale, then their picture would look off. It would look too narrow. The guy's head would be too big. It would look disproportional, right? Which some artists do on purpose. Don't you worry. But normally when they're painting a mural, they sketch it in a small scale first, and then they enlarge it by a scale factor. The opposite of that is people who create dollhouses. A lot of times a dollhouse is modeled after a real house. So they take the dimensions of the real house and they scale it down for the dollhouse. So they're dividing. Their scale factor is going to reduce the figure instead of enlarge the figure. And then this one's pretty cool. This one, it matters a little bit more than dollhouses. So when they're testing a new airplane, this right here is a wind tunnel. First, instead of spending billions of dollars making an airplane, first they make a model of that airplane. Now that airplane, if you're going to test the model out, it better behave exactly like the real thing is going to behave, right? It better have the same proportions. It better be similar to the real one. But you're not going to spend that much money first. So they make the model, and then they see how it behaves in this wind tunnel. Can it handle different things that it would have to handle in the real world, in the elements, but not climate? So they create it smaller. They see how it handles stuff in the wind tunnel. Then they make adjustments, and then they can spend billions of dollars and make the real size. But they would need to know about similarity for that experiment to actually work. So lots of people use similarity in the real world. Kind of already talked about that. Where do these belong? Congruent, similar. Congruent figures are always similar. Similar figures are always congruent. Which one of those is true? Yeah. Okay, so whichever one is harder to be goes in the smaller circle. Like when you're doing darts, the smaller circle is harder to get at. Is it harder to be congruent or similar? You have more things have to be true to be congruent. You have to match perfectly in every way. Similar, it's still hard to be similar. But if you meet all the requirements of being congruent, then you definitely meet all the requirements of being similar. It's kind of like an equilateral triangle and an isosceles triangle. If you're equilateral and all of your sides are congruent, then are at least two of them congruent? Yeah. Okay. Let's talk a little bit more about ratios. A ratio of A to B in math language is technically a quotient. Quotient means divide. It's the quotient obtained by dividing A by B, where B is not allowed to equal 0. We know that, right? That's illegal in math for the denominator to be 0. Can't divide by 0. So a ratio is a quotient. It's a division. A proportion is an equation. So a proportion has to have an equal sign. It's an equation stating that two ratios are equal. So A to B is a ratio. A over B equals C over D is a proportion. Here's what, so that was like algebra review. Here's what I need you to know for geometry purposes. This should definitely go in your notes. Two polygons are similar if ... First of all, here's the symbol for similar. Remember the symbol for congruent looks like this. The symbol for similar is just the squiggly on top. So congruent has an equal sign in it because those figures are equal. Similar just has the squiggly on top. That's what symbol we use to represent it. So here are the two requirements for polygons to be similar. We're going to say something about their angles, and we're going to say something about their size. Two polygons are similar if and only if their angles are congruent, and their sides are proportional. We don't want their sides to be congruent. Well, they could be, but then they'd be congruent figures. Angles are congruent. The angles should match verbatim, but the sides are not congruent. They're proportional. Let's just talk strategy here. We don't need to solve anything here, but let's just talk about what we would do if we were trying to decide if these figures were similar on the coordinate plane. What would we do on the coordinate plane? Because we don't have a protractor, and we don't really have a formula to measure an angle on the coordinate plane unless it's perpendicular, then their slopes are opposite reciprocals, but whatever. So what would we need to check? What would we be looking for? The slopes. But don't you agree, I could rotate that figure, and if it's similar, I mean, it would still be similar, and slopes wouldn't help me anymore. Do you see what I'm saying? Slopes only help because this figure has just been like translated and enlarged or whatever, okay? Patty paper, very good idea. Patty paper would be our friend for sure, and that would check angles. Now, what would we do to check the size? Well, if we were going to compare B, C, and ST, easy, right? We just count how long they are. But to see if two figures are similar, we need to compare more than just two sides, yeah. So you would either need to use the distance formula, or You could make a right triangle out of it and use Pythagorean theorem. This is not slope. This is finding the legs of a right triangle and doing a squared plus b squared equals c squared. So this would be 2, this would be 1, 2, 3. So you would do 2 squared plus 6 squared. And you would square root that. So you're going to compare the side lengths. That's how you're going to know if they're similar or not. But we're not going to go there right now. Let's start with an easier one in the coordinate plane. Are these polygons similar? Yes or no question. Don't answer yet. So one thing you could check is the angles. We are pretty much relying on these being rectangles. We're given that right angle, so we're kind of assuming, okay, it's a rectangle. So their angles are congruent. They're all 90 on both figures, so we've got that one box checked. Now we have to make sure the sides are proportional. When we compare the sides, we want to compare the smallest side to the smallest side, and the largest side in this figure to the largest side. So we would say, does 5 compare to 8 as 7 compares to 10? How do we determine if that's a true statement or not? If that proportional is true or false? That proportion. Calculadora. We have two choices. One, we can divide. 5 divided by 8. 7 divided by 10. Ooh, they're close, but not close enough. Another way I want you to be able to check is by, it starts with C. What do you do with proportions? Cross multiply, yes. And I think this way is easier. I like whole numbers rather than decimals, don't you? 50 compared with, oh no. So now I know that these polygons are not similar because their sides are not proportional. So if I give you a problem and I say 2 rectangles are always, sometimes, or never similar, what would you say? Are all rectangles similar to each other? They all look similar, right? Sometimes, yeah. So rectangles are sometimes similar. They could be similar if their sides are proportional because their angles are all equal, but there are definitely times when rectangles are not similar to each other. All right, second most important part of this lesson, scale factor. So we're talking about enlarging and reducing things, but how much are we going to enlarge it by? How much are we going to reduce it by? That's what scale factor tells us. Write it down. The scale factor of 2 similar polygons is the ratio, so it's usually a fraction, that will transform the first polygon to the second one. It's the ratio. How much bigger did it get? How much smaller did it get? So I need you to walk away knowing that scale factor is second over first. You might not know what that means yet. We'll do some examples, but I want you to think second over first, second over first, second over first. That's scale factor, and that's important. When you know the scale factor and you want to see how much larger or smaller a figure got, when you're going from first to second, you multiply. So I have a calculator, and I'm going to make a large calculator poster for my room, and it's going to, my scale factor is going to be 5. So I could take measurements from here, multiply them by 5, and then I'll know how big to make the poster in my room. So when you're trying to go forward, you multiply. Well, if I already have the poster, and I want to find the dimensions of the calculator, you divide. So you would divide by 5 if you're going from second to first rather than first to second. So when you're going forward, you multiply with your scale factor, and when you're going backwards, you divide. Those are inverse operations. Those undo each other. Oh, we're not going to do class flow today because I don't want to run out of time. Okay, so let's look at A. Find the scale factor, and it's already telling us that they're similar, so we don't need to prove they're similar. So scale factor, we're going from here to here, and we know it's second divided by first. 6 divided by 4. Second divided by first. You always reduce your scale factor. Ms. Tanton, do we have to reduce? Yes, you always reduce your scale factor. I would rather you put scale factor in fraction form. It's not wrong if you put 1.5. That pentagon is 1.5 times bigger. But since scale factor is a ratio, I want to mostly see it in fraction form. And that's how you'll usually see it, like on multiple choice on the test. Okay, what about this one? Be careful which way the arrow's pointing. Second over first. Now this time I gave you coordinates instead of side lengths. So you can pick your x's or your y's. It doesn't matter. Second over first. Second over first. -8 divided by -2. The negatives cancel. How much bigger is that second heart than the first heart? 4 times bigger. Okay. Last one. Second over first. Second over first. 2 is the second figure, comes from the second figure, isn't it? And 7 comes from the first figure. So 2/7 is the scale factor. Now I want you to notice how the scale factor compares to the size of our dilation. That's what these are, they're dilations. Okay, in this one it was an enlargement. And my scale factor is 1.5, 3/2. On this one it was another enlargement, and my scale factor was 4. On this one it was a reduction, and my scale factor is 2/7. So, yeah, so what we can conclude is that if our scale factor is greater than 1, our figure is getting bigger. If our scale factor is less than 1, our figure is getting smaller, and our scale factor, believe it or not, can equal 1. If your scale factor equals 1, it's called a congruence transformation. So you can dilate a figure by a scale factor of 1, but you'll get another congruent figure. This is just for fun, so we're going to go really quickly on this. Believe it or not, when they make Hot Wheels, I've seen the making of Hot Wheels or whatever. When they make Hot Wheels, they go to the real car. They take thousands of measurements from the real car, and then they scale all of those measurements down by the exact same scale factor, by the exact same ratio. So that way, the Hot Wheels car looks proportional to the real car. They're similar. Their size, their lengths are proportional. So they use similarity when making Hot Wheels. Now, what's that number? How much smaller is the Hot Wheels car than the real car? How much bigger is the real car than the Hot Wheels car? Can you take a guess? They use, Hot Wheels, the company, uses a scale factor of 1 to 64. So here's what I meant when I'm saying you go forwards and backwards. So if you knew that this was, I don't know, 14 feet, then what would that length be on the toy car? You're going backwards, right? You're getting smaller. So you would divide. If you're getting smaller, obviously you divide. If you're going forward, you multiply. So you would do 14 divided by 64, and it'd be some, decimal, and you could convert it into inches or whatever, but I don't care. So you would divide it 0.2 feet, whatever. We could convert that to inches. Now, if I told you that the height of this one was 1 inch, and I wanted to know the height of the real car, I would multiply it 64 inches, 1 times 64. So I mean by going forwards and backwards, and we'll see that again in some other problems. All right. If triangle bat is similar to, that's what this means, is similar to triangle mitt, solve for x. Now what's important is that normally on these problems, we set up a proportion. 3 is 12 as 4 is to x. But I made a huge mistake there. What did I do wrong? They're not corresponding. I love how you use the word corresponding. These were not corresponding sides. Ooh, you remember how CP, corresponding parts of congruent triangles are congruent? Let's make up a new one. Corresponding parts of similar triangles are proportional. Whoa. CPSTP. I just totally made that up. I've never done that before. Okay, anyway. So we can't compare this. What I would do if I were you is use Pythagorean theorem and find IT. 3 squared plus 4 squared is 25. Square root of 25. Phew. Now I have corresponding parts. 3 is to 12 as 5 is to x. How do you solve for a variable? How do you solve for a variable in a proportion? Cross multiply, right? 5 times 12 divided by 3. 5 times 12 is 60. 60 divided by 3. Final answer. Now, you don't always have to solve these using a proportion. You could have started this problem by finding the scale factor. Okay, now we have to look at the order here. Triangle bat is similar to triangle mint. So this one's our first, and this is our second, listed in order. So the scale factor, second over first, 3 over 12. So what's the scale factor? It got smaller. It got 4 times smaller, even though it's not drawn to scale. So what I was saying earlier is that when you're going forwards, you multiply. So like, how do I get from 12 to 3? I just multiply by my scale factor. 12 times 1/4. But if I wanted to go the other way, I want to get my answer. Then I do 5, and then I divide by my scale factor. Dividing by 1/4, just to let you know, is the same as multiplying by 4. Just do 5 times 4. That's how we could have gotten our answer in the first place, 20. And then we wouldn't have had to cross multiply. Okay. We're going to skip this one. We're going to go to this one. These two tablets are similar. I think they make tablets much skinnier now, so that clip art is out of old. What is the perimeter of the larger tablet? So you can do this the scale factor way, or you can do this the out of style, or you can do this the proportion way. I go straight to proportion if I can see that my scale factor is not going to be a whole number. 14 divided by 10, sorry guys, not a whole number. So I like to do proportions when it's not a whole number. So I'm going to do second over first equals second over first. Just be consistent when you're setting up your proportion. Yep, you could have done 10 is to 14. That works too. You could have done that. So now we're going to cross multiply. 14 times 7 divided by 10. And we get 9.8. So now you know how to find the perimeter. You add up all the sides. So 14 times 2 plus 9.8 times 2. So the answer to this problem is 47.6. And this is our first unit. Our first unit of study that has units in it. There's going to be a lot of units in this unit. So please make sure you put your units when you're in this unit. Inches. Okay. Not always. I'm shopping for tablets right now because we need some. And the screen size is like 9.7. That's not whole numbers. Okay. How would we find multiple missing sides? So, we need to find some corresponding sides. Good. We need to find a ratio. Yep. We need to set up a proportion. That's going to be our key. We're going to use that one every time we solve for a missing side. So I would say, like, 30 is to 18 as, who do I want to use next? This guy and this guy. As 25 is to x. And then we would use it again. That's our key. 30 is to 18 as 20 is to z. And then we can use it one more time. 30 is to 18 as, oh no, squiggly, there we go. Y is to 15. So once you find two sides that correspond with one another, you can use them multiple times, and you're just cross multiplying, cross multiplying, cross multiplying. We're not even going to solve it. Good job if you solved it. Okay. Last problem of the day. I'm going to let you think about this one. Let me know when you have an answer. So we have to make sure that we are matching up the corresponding sides. So when we look at these rectangles, first of all, so we're comparing the green one to the red one. Let's just keep this one red. And one thing we know about the green one is that this is 2, right? Yeah, because we can just slide that length over, that height or whatever. So in my red one, my short side is 2. What's my short side in the green one? So it's really important that you're matching up the corresponding sides. This is my longer side in the red one. This is my longer side in the green one. So what I want to do, the circle over the circle equals the square over the square. See what I'm saying there? You have to put the shorter side over the shorter side and then the longer side over the longer side. When you do that, it was kind of confusing to set that up, but now that we've set this up, this is easy. 2 times 2 is 4, and we divide it by that one, 4 divided by 6. So the length of x is a fraction, it's 2/3. We write it as a fraction, not as a repeating decimal.